Oh, oops, fail. I forgot to switch the microphone on. Hopefully you can hear me now. Thank you very much for joining me, and welcome to Practically in the morning. Oh dear, I look a bit sleepy, sorry. So thank you very much for joining me on this Practically live broadcast. It is a live broadcast, so anything can happen. And today we're going to continue looking at the Brave Clojure, as we've done for the last couple of broadcasts. We're going to continue looking specifically at chapter 3, where we started last week. We covered things like conditionals and just basically understanding this concept of forms. I still have a little bit of cold, sorry. And so this time we're going to look at data structures, which are really cool. That's one of the things I really appreciated as I started to get to learn Clojure. You don't need to model, you don't need to create a whole bunch of classes or these other structures to model the system you're building. You can literally just define data structures or a data structure that you're using, and then you write functions to transform that from one structure to another, or like put extra values in, take values off. So especially the built-in data structures that we're going to look at today are kind of very central to designing and working with Clojure. Okay, so before we just get started, let's just check all the buttons work. Oh yeah, screencast. Ooh, nice. So this is the website, hasn't changed much. I do want to change this. I had some feedback to try and make this better. If you've got any design ideas or skills, let me know. This is how you can support me. Thank you very much for everybody who continues to support me by subscribing, send me donations. Again, a lot of the work I do is at the weekends now. Although I do have a job now. Yay, thank you very much for hiring me. You can reach out to me at these channels, whichever. I'm on all three of them, so you can kind of, these are the main places. So there's a lot of discussions around, in general, about Clojure on Clojure in Slack. There's a big data science community on Clojure in Zulip. And Discord is there just to see what it's like, but there's kind of some healthy discussions on there as well, so feel free to use whichever you prefer. And I'm going to add a Brave Clojure study group playlist as well, although you can find everything under the Clojure study group playlist that we've done so far. Okay, what are we doing today? The Brave Clojure. Again, you don't have to be brave or true to do Clojure, but it helps to have a little bit of courage when you're doing coding and when you're learning a new language, because it can be simple, but it's not always easy. Oops, where is it? Chapter 3. Oh, I did put the link into the chat where we are today. I'm going to copy that. Nope, that didn't work. Oh, that's the wrong link. Oh dear. Oh, there it is. That's the one. That's what we want. Oops. Oh, there we go. So we started this last week where we were looking at forms. So forms is just like Clojure, Clojure forms that actually work. So form is a piece of Clojure that actually works. You can evaluate it, and we did a lot of the conditional stuff with if, when, and or, and. We also touched on naming things, so we can bind a name to a value. So this is kind of like assignment in other languages, but you've got specific syntax there, so we're not overloading the equals for assignment. We can keep equals for equality, which is nice, which simplifies the syntax of Clojure. And we look briefly at functions as well, although we're going to cover functions as a different section as well. So data structures, nice. So what is a data structure? Well, we've seen values that we have. We can think of a data structure as a value. It's just a more complex value. So rather than having a string, so we've got a string here, which is like a simple value. It's just self-contained, although you can treat this as a sequence of characters as well if you wanted to. We've got like numbers, they're very simple characters. But if you, so you've got things like numbers and strings, which are very simple things, and you can kind of bind a name to those values as well. But then we've got more interesting data structures, such as list, map, vector, and set. And so, yeah, I don't think we need to cover the numbers. The numbers and values are self-explanatory, although there is actually one interesting thing. So let's just do a quick thing with numbers. So this is a project, it's just a simple Clojure CLI project I've created. I'm just updating it with the things we've been covering in the last broadcast, so I'll push this out today so you can see that. Yeah, so we like just covering the basic forms of things. I just need to tidy up the flow control and things we did with that. And then we've got data structures. So we're going to look at things like, like the built-in data structures. If I can type, oops. I got typed there. There we go. Immutability. I think the data structures is a good way to understand immutability of things as well, especially when you start working with them and change them, because you're not really changing them, you're just making copies. And so we're going to look at strings, keywords, and then the data structures themselves. So let's look at numbers. And there's a really nice link. There's a really nice reference page on the Clojure.org website, which covers numbers, which I have open here. So this gives things like nil, which is a perfectly legal value, and it's actually quite a handy way to pass back a value because nil is treated as false, like a logical false. So it's a really nice value to pass back. And if you don't pass anything else back, then you're passing back nil by default in your functions. And there's also this idea of nil pointing, where you, like, if you want to check something, if you want to check if a collection is empty, as a data structure is empty, you just use seek, and that'll return a nil if the collection is empty. We've got different types of numbers, but essentially we can do all the normal arithmetic, and there are some maths functions there as well, and so plenty of related functions there you can take a look at to understand how to do kind of maths. Yeah, you can even do like really big mathematics. You can use some of the Java libraries as well, which help do mathematics. They're really good, and again, we're still dealing with immutable values there, so they work quite nicely. Strings and characters, keywords. We're going to look at these when we come to maps, essentially, but a keyword is just a kind of a thing that points to itself. So it's very useful for lookups and just defining a self-contained value, because the value of a keyword is the keyword itself. That might not make sense to you until we actually see some examples, so don't worry about that. And then we talk about collections, which is where we start to introduce things like lists, vectors, maps, and I don't think anybody uses struct maps. I've never actually seen those. If anybody does use them, I'd be interested to see what you're doing. and then sets. Okay. Oh yeah, one thing I just wanted to mention. So this one thing is fairly unique. I don't think I've seen it in other languages yet. There may be some examples, but there's this idea of a ratio type. So if I divide, for example, 22 by 7, in most languages you'll get like the floating point value, so you get like 3 point something. In Clojure you get 22 over 7. And why is this useful? Well, it's, as the title suggests, it's lazy precision, which I call it. So we're actually not kind of working out what the value is, like like so many decimal points yet. We're leaving that decision to a later date, or not even taking that decision. What we could do is, like, so if we have that value, but then we want to multiply it by something. Example, let's take a very simple example, and if we want to multiply that by 7, then it actually cancels the division out. Whereas if we did this with a decimal number, then that would basically cast the result of this nested expression to a decimal, and then we may lose some precision there. In this case we don't, because it's quite a simple thing. Let's do that with 9. Yeah, so we might have lost some precision there. We don't know what's happening there. If we take that off, yeah, if we take that off, we definitely haven't lost any precision yet. We just need to we can still pass this round as a value, because 198 over 7 is actually a value, just like 1 is a value. 198 over 7, I think it was, is a value, and yeah, it's just like any other number, except this is a ratio type. And so we can again decide when we want, if we even want to get a decimal figure out of that, decimal point figure out of that. Okay. Strings of characters. So this string is quite a curious thing, because it's not really a data structure, but you can treat it as a data structure, because it's a collection of characters. So if we do, we want to find out whether Racecar is what's the word? Not polynomial. Is the same forward as it is backwards. Somebody remembers what that means, what that word is. Please let me know. I think it begins with P. So if we did a reverse on that, which is a Clojure core function, then we actually get Racecar back again reversed, so we can kind of see it is the same forward as it is backwards. Although you notice it's not quite the same shape. We're actually getting a sequence of characters, so that's how that's treating. So a lot of the Clojure core functions treat a string as a collection of characters, and then there are Clojure.string namespace, which is specifically works with strings. And there's a whole bunch of things in here. Oh, even a reverse and split. So there's quite a nice collection of functions specifically to work with strings, and they will specifically keep the thing as a string. You can do things like joining them again. If we did a apply structure to reverse, so we're taking the the sequence of characters that this is generating, and we're basically applying string to each one of them and then concatenating them. So basically concatenating each character together into a single string and return the result. So sometimes you'll see this, but I think the more idiomatic way is to use Clojure string, especially if you're dealing with if you're using this Clojure string namespace already. Then yeah, you should use like Clojure string join, I think it is. Yeah, join, and that also allows you to include a separator as well, so you can like join things with commas. If you want to generate a comma separated value CSV file, you can do that very easily. Palindrome, thank you very much. Thank you for filling in the gaps in my brain. So if I've got Racecar, there we go. I like to make things interactive to give the audience something to do. Let's just make that there. Yeah, so string join will join them up. So that's the equivalent of doing apply string to the same kind of sequence. Okay. So mention keywords, again, we'll look at that in, I think it makes a lot more sense to think about them when you're dealing with maps. Let's just look at the list structure. So we've been using list structures all the way through so far, because every time we're calling a function, we're using a list. And what we can see here is that whenever we use a list, then the first thing inside that is going to be interpreted as a call to that particular function. So this is a name. In this case, it's a fully qualified name because we're including the domain, the names, the full namespace where that function lives. So this is the directory structure as well as the namespace and where that file lives. They're the same thing. We don't need the fully qualified name for applying string because they're part of Clojure core, so they're included in our environment already. So we can just use them by their specific function names. But if we want to use a list as a data structure, then we can also use this quote. So we can use quote 1, 2, 3. And that's going to return 1, 2, 3. It's just returning the list as a data structure. Whereas if we evaluate 1, 2, 3 by itself, then we get we're trying to cast. It's saying it's trying to cast an I function type to. Well, we're trying to take a Java long and use it as an I function. Basically, that's what it's saying. Yeah, so Java Jang long, which is what the one, this is the type of the one value, can be cast to Clojure line IFN. And IFN basically means a type that implements the function interface. So I for interface and F for function. So if you see this, it means you haven't got your brackets right, or you've tried to use a list as a data structure without quoting. If you see that a lot, don't worry, because I used to do that lots of times as well, but it does give you a quick reminder. And if you're using CLJ Condo, which I do recommend, then it's also giving you a very simple hint that we're actually using a number as a function when we shouldn't do, because 1 is not a function. That would be very strange syntax if it was. So we can use quote, and we can also use this little single quote, which is a shortcut for that calling the quote function. So these are just the same, exactly the same syntax. This is just the short form of doing it, and this is what you will see more often. Very rarely see anybody actually using the quote explicitly typed out here. Just using a single quote is more efficient. So although we use the list extensively, it's not used as much as an explicit data structure. So when we're defining our own data structures, we tend not to use lists that often, and partially because a list has another context. It has this function call context as well by default, so you're always having to escape that. But there are also some other interesting aspects. So this list is a linked list, so this value is pointing to the next value, and to get to the next value, that points to the next value. So you have to traverse a list sequentially. You can't jump straight to the end or somewhere in the middle. There's no underlying index values for this collection. But there is, so it's not really like an array. It is like a linked list. In that each value in the list points to the next value, and the only way to traverse it is to follow all those links. But if you want a vector, but if you want an array, you can use a vector structure. So that's just the square brackets, and we don't need to escape this. This is a kind of difference between Clojure and other Lisps as well. We use square brackets and curly brackets to denote some of the other data structures. And this has an index, so we can do things like we can get I think this is right. My brain, can we do that? Yeah. So here we're getting the value from the vector, which is at the index of 2. And if you've done any programming before, you'll know that like typically indexes start at 0. So that's where we get 2. So the index of this is 1 is at index 0, 2 is at index 1, and 3 is at index 2. So that's where we get the value there, 2. And another interesting thing is that these vectors get treated like sequences as well. So if we want to compare a vector 1, 2, 3, it's actually the same as the list type 1, 2, 3. So even though these are different data structures, because they've got the same values, we're treating them. We're trying to understand whether they're equal in terms of the value that they represent, not the structures that they're actually in. I think this is one of the getchers. People like see that their functions are returning a sequence of values, and then they think that they need to change it back to a vector, but actually these are equal as well, because the values that they contain are equal. If we had different values in here, then obviously they're not going to be equal anymore. Let's see, where do we go? Where did we get to with the book? So we've covered those maps. So what's it doing with maps? Yeah, so maps dictionaries. I like these kind of things. So if let's see, let's have a look at maps. Maps. So in some languages, these are called dictionaries because you can look up. I haven't spelled that right, if I know. You can look up a thing and it tells you what it means. That's kind of like if you get an English dictionary, then it will tell you the meaning of the words. That's not right. There we go. That's not right. There we go. Oh, I can't spell. And so this is quite a useful concept for creating a very simple lookup table. So if we go to Clojure exorcism, Oh, maybe it's in exorcism. There we go. Exorcism. Clojure. One of the examples in here is this RNA transcription. And if we go to source, there we go. So one of the things to do here is to convert between DNA to RNA. And essentially there's just a simple mapping between that. So if we have a letter G in our DNA sequence, then that's that actually is C in RNA, and C in DNA is G in RNA. So we can actually look these up because these are our keys, and each key has a value. So if you look up the key, then you can actually get the value of what it looks up to. So in an English dictionary, this would be the word you were looking for. So if you wanted to look up palindrome, then this value would be the description of palindrome. And you can also treat this map in reverse as well. So if you wanted to go backwards, you can just reverse this map, and then you can go from RNA, which if it's C, then it's G, and if it's G, then it's C, and so on and so on. So it's a very simple way to do that. And how am I doing that? So basically, yeah, I'm just calling the map. So I've called this DNA nucleotide to RNA nucleotide, calling that with a character from my DNA string. And if it's in there, it's just going to return the value. And if it's not, then it's going to throw like an error for me. So this is a very simple way of doing this. Can we start a REPL? So this is a very nice way to define a dictionary approach. You could also think of this as a very simple state transition as well, because you're basically defining, we're going from an initial state to a new state, so you can define that as a state transition. You could also have these values as functions you were calling as well. Ooh. Sorry, thank you. The button doesn't always work. Yeah, so I'm going to take this string of characters and pass the map over it. So passing the dictionary over it, and for each character we come across, it's going to return its equivalent character in the map. So that's a really cool way of using hash maps. Good. Look at maps. And there's a whole bunch of examples here I've done. So maps are quite good for defining meaningful and kind of self-describing data structures. I mean, this is almost like an object, but without all the ceremony you would have with an object. So here we've got a map defined by the curly brackets, and then we've got keys in the map. So these are almost like the fields in a database, because they've got a value, and the value can be a simple value like a string or a number, or we can also include another data structure. So here we can kind of build up a nested data structure here. So we've got this is a movie, Empire Strikes Back. I'll leave that to you to decide if that is the best movie. And then we've got an actors key. And here we're actually using these keywords. So a keyword is kind of a name that has a colon at the start of it. And so here we're defining characteristics. Here we're defining characteristics of a movie, and so we can go do as big and as complex a map as we actually want to. And we're just using def here to define a name for it, so we don't have to type it in the map or copy the map around explicitly. We can refer to this map with the name, and then we can refer to that. We can pull out values from that map by getting the key, and then that will return the associated value from it. So we can use the get function, which is explicitly saying get from this map where the key is name, and then return the value that name is pointing to. So again, name is associated with the string, and this is why a map is called an associative data structure, because it's associating a key with a value. It's back on again. There we go. So the nice thing about using keywords for keys is that you can do shortcuts like this. So you can, instead of having to use get, we can actually use the keyword as a function. So this is quite a nice thing, and it works with most data structures as well. If the key is a keyword, you can use that as a function with the map. So best movie is a map. So this gives the same results. You can also do best movie. Oh, yeah. Why is my structural editing not on? There we go. Yeah. So if we've got best movie, we could use that as a function. So we're actually using the map itself as a function, and we give it a key, which is actors, and this is returning the value that actors points to within that map. So we don't always need to use get, and why would you use this shortcut? If you're mapping over this, if you were mapping over a get, so if you're using map over some kind of data structure, then yeah, it's nice, and it's slightly simpler to read if you just use the short form either way, or you can also do other things like you can use a threading macro if you really want to, and you can, oops, that's not right, to pass the map, which is best movie, over actors, and you get that result. So you can use get in to kind of walk the data structure. So instead of just using get, we want to get in. We want to navigate through the data structure, and first we pull out the actors, which is going to return a map, and then we want, from that map, we want the value that is pointed to by the lia keyword, so the lia key, and keys can be strings and numbers and other and even data structures. So here it's pulling out the specific thing. And we can also use the threading macro. So this thread's in here. We can take best movie, We can thread that through actors, and then oops, Leah. I think. Oh, actually, no, that might not work because it's not a keyword. Yeah. So that if we have all keywords, then we can use the thready macro. But because it's a string rather than a keyword as a key, then we've got some limitations there. So using keywords in using keywords in your map does allow you to do extra things like traverse them in these nice little ways, like using threading macros. Anything else in here? Oh yeah, so we can do some iteration over maps. So here we've just got some project management tasks, whether they're CapEx or OpEx, so there all seems to be CapEx. And then we can kind of do for loops over them. We can go and get in projects. Oh yeah, so we're looking at project A in here. Why doesn't that work? Oh, what we're doing? Oh, okay. Maybe that's not a good example. There we go. Oh yeah. I'll kind of put some example. I'll tidy this example up and cover that another time. But yeah, so designing a map is quite it's a bit of an art form. Again, it's coming up with like a nice data structure here, not making it too nested as well. That's useful. Try and keep it as flat as possible. But sometimes you do need to nest it because it just kind of makes things nice. And if you can kind of flatten them, you can also put them into a vector and have lots of like a vector of individual maps that you that then process. And then each map is just an element you process. So what do we got here? This example, yeah, so we're using that. So we can use any kind of thing as a keyword that's legal in Clojure. So here we're using strings, keywords. We can also use like things like a vector as well. So we could have here. We also use a vector of like one and three. I can't think of a good example now. I think I had one in my head a minute ago. Yeah, so they're quite flexible in what you can use for keys, but it's what comes down to what makes it easier to actually use the map as well. So there is kind of like an art to designing these. It's like it's where you put in a lot of thought about designing your structure, and ideally it's quite useful to combine like defs. If you've got a number of defs that are actually have data that's related to each other, then putting them in a single def is usually more easier to work with, because then you've just got a single map to work with, and it's usually often better to have a single map which all the functions work with, rather than having lots of different maps and kind of different functions working with different maps. It's a simpler design when you've just got a single kind of map to do these things. What are we doing? So we've covered maps, keywords. What are we doing here? Oh yeah, so here we're using the keyword as a function. Here we're using get. So yeah, that covers that in the book. We can use vectors. So we mentioned vectors are similar to an array. The kind of difference really is that in most languages, which are like mutable by default, then you kind of grow the vector. Whereas here we kind of, once we've created a vector, then that's fixed. So we can't change the vector, although we can apply functions on it and get different results. Sometimes those results are going to be part of that data structure, sometimes they're not. So if we've got, yeah, so what it's doing, we're doing get, yeah, that's the example I did earlier. There we go. So yeah, we're just getting the index of 0 from the map, and it returns 3. We can also use get in here as well. Let's go to 3. Yeah, space. Study group. Oh, that's not wanted. No, there we go. Vectors. Yeah, so we've got, this is our vector. We're still using the get function because it's like get is just working over a collection, which is like a general term for all these data structures. And so A is our key and our map is our value. And we're getting, we're asking for one. Oh, sorry. Yeah. No, it's a vector, isn't it? So these are our values. So we're no longer kind of associating the values together. Well, so we're not associating A with the map. We're actually just having these associated with the index. Ooh. Yeah, I wasn't talking then, sorry. Yeah, sorry, I've got a bit of a cough. I meant to switch the microphone off, so I'm not definitely new with my coughing. So we've got the this vector, which is we have this vector, which is a collection of values, and they all have this index underneath them. So this is index 0, index 1 for the map, and index 2 for the string C. And we can get them using the get function. But again, we can also use the vector itself as a function call. And we give it the vector an argument of 1. And then it goes up and finds the value that's at index 1. So this is index 0, this is index 1, and it returns a result. So this gives the same result as the line above. That's the wrong button. There we go. So again, it's when you're starting, it's probably more comfortable to use the get, but you may see people using the vector or the map or the data structure as a function call as well. So hopefully that doesn't confuse you too much to start with. It is fairly common to use get, but this can be kind of a nice shortcut sometimes. Oh yeah, contains versus sum. So there is a function called contains, and there is a function called sum. There's quite a few actually, contains doesn't always work as you may expect. So if we contain, actually if we use the same data structure, it's useful to be aware of where what it means by contains. So this is wanting a collection and a key. And so if we do 1 here, it's not checking to see if the value 1 is there, because it isn't. There's no value 1 in the vector, but it is checking the key, and for a vector, the index is the key. So underneath here, there is like, yeah, the key. This is this index. That's 0 index. Oops. This is 1. Oops. Oh yeah, and this is 2. So if we try and find a value, so we change this to a, which is in the vector, but it's not a key. So using contains can be a little bit confusing if you don't understand, if you haven't kind of, yeah, if you're looking for a value rather than the key. Is it some? And what's the thing for that? So he wants a predicate and a collection. So we do a. That's not quite right, because that's not how we define a predicate. If we wrap this inside a set. Oops, that's not quite right. Yeah. There we go. So we can use sum instead of contain. So this is one thing that kind of does trip people up when they're first starting. Contains using. So this is looking up via a key for the data structure, and this is looking up. Oops, that's not right. Up via a value. So basically, if you want to find something by its key, then you would use contains. If you want to find something by its value, does it exist inside does that particular value here exist inside the map, the vector, sorry, then you would use sum. And if we do that, so if we use a value that's not there, then we get nil. So that nil is another example of that nil value being false, like meaning false. And we refer to that usually as falsy, because it's not a specific false Boolean name. So we've got true and false, as we covered last time, which are specific Booleans that return true and false. Oops, if we evaluate them in the right way. So that's true, that's false. So these are values themselves, and so it's nil. And when we're using sum and we don't find something, then it returns nil so that we know it's false. When it returns true, it returns the value that we were looking for. So it's a very nice way to kind of say, yes, it's true, and here's the value back, so I can actually just keep on using that value. Okay. Oh, wow, that went quick. So we've kind of, we briefly mentioned lists, and we've mentioned vectors and maps. Vectors and maps tend to be the ones you use the most when you're developing stuff. So you would, when you're defining your data structure, then like common examples are like having a vector of a whole series of similar values or similar structured values. So you might have a vector of maps that all look the same. Boom, boom, boom. Boom. So you'd have like on and on, you'd have like a collection of this, and this makes it very easy, so then you could just iterate over these values that just happen to be maps, and do some like batch processing and transform them. So this is kind of like doing, I guess it's a bit like doing SQL statements over a database. It's that simple, and so like having a database as flat as possible. That still holds kind of thing when you're defining Clojure data structures as well. And so even if you have to include like some extra fields in there, sometimes it's actually nicer to do that and keep this very flat structure, because then you can process all these values the same. You don't have to keep track of how many of these you've got. You can just keep on processing until the end, or until you meet some condition that you put around this as well. Oops. Clojure to contents. There we go. There we go. And then you can go the other extent, where you're just basically creating a map. So this is very detailed and very self-describing data structure, and this can be quite useful to if you're kind of always updating like key value pairs. So if you've always got like a lookup for a particular key and a value you want to change, then this works quite nicely, because you can just navigate to a particular part of the structure. And you can actually just pull out individual parts. So if we wanted to just have characters, then we could just pull out this string. So we just get characters from that would return another map, and then we could just work with that map. So we could actually pull out some of the nested aspects of a map and work with them, so they're kind of a lot flatter. So actually just building out this Rebel Alliance ships, we could pull that out and we would get a nice flat vector that we could very easily process without having to worry about what else is in there. And if we wanted to make a change, then we can also always update the map by, again, using the key and key references to find the right place to update that value. I'll put some of these examples in that other project, in this Getting Started project, to give you some examples, and then I'll publish that later on this weekend. What else is in the book? Oops, there we go. Oh yes, and then I think this is quite an actual simple way to understand immutability inside data structures, because we haven't talked about that, and I did say we were going to. Apologies. So immutability, which is the opposite of mutability. So a lot of programming languages are mutable by default. So like if you change something, it actually changes the thing in memory. Whereas in functional programming languages, then you tend to make a copy. So if we do conj, so we're just conjoining. So we've got an immutable vector here, so we can't change the vector, but yet we can still get the result that we want. So it looks like we're changing it, but we're not actually changing it. We're actually creating a copy. So we're actually creating a new data structure. So this is a new data structure we've created, and the old one is the same. So an easy way to demonstrate that is to do def my data. So we've got data here. Boom, boom, boom. So we define that. So we've got my data, which is a reference we can do. So we can use conj or cons or many other functions that will allow us to transform a data structure. Let's do 4. There we go. So this is going to give us that result again. Not surprisingly, hopefully that's makes sense. However, if we go and look at, if we go and conj, we go and conj with my data again, and we do a different value, then the 4 that we added previously isn't there, because we haven't actually changed this underlying data structure. So this 1, 2, 3 hasn't changed. And this means that we can actually give this to a huge number of functions, and they can all work with it independently. They don't have to worry about what all the other functions are actually doing with this data. It's shared between them, but as it's immutable, each individual function can't change it for the other functions, which makes your code so much simpler because you don't have to worry about side effects from other functions. You can just say, okay, I've got a bit of data, I'm going to work with that, I'm going to do my thing with that data and generate a result. And then you might feed that back into other functions, and they do their thing, and then they do that. So you're always getting kind of a known input in here because other functions aren't creating these side effects that could change something. Because if this conj did change the contents of my data, then when we call my data with 7, that would be affected. So we'd actually have a 4 in there as well. So rather than mutating values, we pass that data around. So if we go to Practicalli Clojure, introduction. There we go. So this is a very simple diagram. So like in an iterative, in a imperative language, then you'd have like these functions, these methods interacting with variables. So there's mutable values. And in programming languages, you would pass, you might take an input as a data structure, and then you would do something with that data structure, and then you pass the result to a function. But then the other functions are not interfering with that argument. That argument is kind of an immutable value that's passed there. It's not going to change, but the function can do something with it, and then create a new argument that gets passed to another function, and so on and so on. So the values get passed around And so the function, each of these individual functions are very easy to understand because given the same argument, they're always going to do the same thing. So they're very deterministic. But it does mean you are thinking about passing values. So a function should always have the values that we should always pass in all the arguments that it actually needs to do its work, rather than trying to sharing them wherever possible. And if you are going to share them, it is possible to do that, but it's you do have to be more careful when you do that. But ideally, you would pass in all the arguments as immutable values, and then your system is just really easy. You can actually understand the individual functions and sort of build up your knowledge of the system that way. How are we doing? Oh, we're at time already. Let's see what else there is to cover in the book. Lists, we've already covered lists. Anything else in lists? No. Sets, we didn't cover sets. Well, we kind of briefly did because we used a set as our predicate. So sets are a collection of unique values. So here we've got two ones and two twos. And when we turn that into a set, using the hash set thing, then it's generating a nice set for us. Let's just have a quick look at this in the editor. Oops. So that gives us the value that we're wanting. That gives us this unique value, and we can express sets directly as we did in, if you remember all the way back to a few minutes ago, we defined this B as a set. So we can use sets as kind of predicates as well, which is quite nice. But if we want to, yeah, we can express them specifically. So we just type them in and that's okay. But if we express them as a literal value, then that's going to be an error, because we can't have duplicate values inside the set. And here it's saying we got a duplicate key. So if you've got values that you want to make sure that they're unique, you can use the hash set in there as well. And I think, oh yeah, if you go back to Clojure through code, I do have a, oops, no, that's all right, common words here. And so this is this is pulling in some common English words in a comma separated values, so in a CSV file essentially. And what we're doing is using a set to just make sure that they're all unique, because we don't want to have duplicates in there. It just makes it inefficient to use it, because we're using this to basically pull out the common words from all the words in a book. And so we just make it using set to make sure that those words are unique in there. So we basically pulling out the words in the book and splitting them up on the comma. So it's just basically a series of strings words, and then we just make sure that all those string words are unique by just using set. So that gives us a nice set value there. What have we got? And we can conj. Oh yeah, so yes, so the Clojure core functions are kind of quite intelligent. They are detecting that the B is already in there, so it's not adding a new one. And we can check. So you may have noticed when I was doing this, oops, let's go back to tab, there we go. When I did this, it's saying duplicate key in the error message. So actually each of these values in the set are the key. So they're like keys and values in that sense. And so that means that contains actually just works as you would think it works by contains returns the value, because the value is actually a key inside there as well. So it's not using any index, it's using the individual values in the set as keys because they're all unique. That is the essence of a set, is a collection of unique values. So then the values themselves can be keys because there's never going to be two keys the same. That's quite nice. Oh yeah, and then there's just a comment saying, yeah, it's better to have 100 functions operating on one data structure than 10 on structures. And I think that just makes it simpler and easier. But you don't always create a single data structure up front. Sometimes you'll create a few defs and then realize you can join them together in a meaningful way. That's perfect. That's just part of the evolving of the design. And that's it. I think we've covered everything I was going to do for that section. And then next time we'll look at functions in a bit more detail. Hopefully that was useful. If you've got any more questions, feel free to carry on the discussions in the section, in the contact section. Any of these channels, we'll discuss those. And then I shall put up I should tidy this getting started project up and push that later today, hopefully. And then you can kind of follow on with some nice examples which you can just evaluate in your own REPL. Okay. All right, thank you very much for listening.